that we've done in the session last week, and where I also sent you the link to this little online thing, where I want you to go through these videos that I've prepared for you about kinetics, because why is it important? What's in for you? Well, if you understand these things, then next year you are going to have some stuff on growth curves in a microbiology module, and you'll find these growth curves then very easy to deal with. Also, in your final year, you are going to have some special sessions on reaction kinetics, because that's one of our focus themes in the School of Biosciences. And if you know a little bit about kinetics in the first place, then you shouldn't have any problems. So let's get started with kinetics again. And I think in the last session, I showed you the general rate equation for a reaction, where we have, for example, the rate of a reaction equals, and now it depends on whether we look at the consumption. So for example, if A is consumed, and I write that simply like that, if A is consumed, we have a negative sign. So rate equals negative rate constant times the concentration of A to the power of M. And this M here, that's a rate order. And the K here is the rate constant. And this one here obviously is concentration of A. Okay? Now, one thing that people usually find quite tricky to deal with, if I ask them, how do you find actually the rate order of a reaction? Now, if you know a little bit of maths, that's terribly easy to deal with. Because all you need to do is you just simply say, okay, this negative sign here, that's a little bit awkward. So what I just simply do is, instead of rate, which has a direction, I just simply take the speed, which of course is exactly the same as the rate, but doesn't have a direction. So speed equals K times A to the power of M. So how do I find M? Any ideas what you could do? You look like you are trying to say something, or are you sighing? Log. Absolutely. We log both sides. Bless you. And you would usually use the log to the basis of 10, but you don't have to. You can use any kind of log, because what you then get is log speed equals log K times M log A. Right? Or you can write this in a slightly different form. You can write this as log speed equals M log A plus log K. what you see here is that's the equation for a straight line. Actually, if we just simply say this log speed, that's y equals mx plus c. So if you've got data for that, what you can do is you just simply plot something where you have log speed on the y-axis, log a on the x-axis, and you get a straight line. The gradient of this straight line is our m, that's our rate order. And this point here would be log k. So that's, in a way, how you can graphically find out, if you have a set of data, how you can graphically find out the order of a reaction. That makes sense? Pretty much, I would say. This is actually one of the quizzes where you have to do these things, where you have to find out the order of a reaction. And we said for the order of a reaction, m can be basically anything. Can be any number. It can be a whole number, it can be a fraction, it can be positive, it can be zero, it can be a negative number. M is just simply a mathematical expression that helps us to describe how the speed of a reaction, how the rate of a reaction, I should say, how the rate of this reaction actually depends on the concentration of a reactant. That is what M does. It doesn't tell us anything about how many molecules crash into each other or something like that. Okay, happy with that? Yeah, you're happy with that. Now what I want to do with you today is I want to discuss two very common rate orders. And they are very, very common. And I want to illustrate that with an example. Now let's say for the first rate order that I want to discuss with you, I have sweets. No? No sweets? No sweets. What's wrong with you guys? Don't like sweets? Let's assume I've got 100 of sweets, exactly 100, at time 0. And I say that I can eat, let's say, 10 sweets per 2 minutes. Okay, got that? At the moment, I don't have enough hands. Hold that for me. So I need to demonstrate that, how I eat these sweets, because otherwise you don't believe me that they are sweets. Uncle? Now I can eat 10 sweets per 2 minutes. How many sweets have I left after 8 minutes? Anyone? 60. You said 60? Well done. How did you do that?
So divide 8 by 2, 4, so 4 times 10 is 40.
You divided 8 by 10
By 2.
by 2. Oh, okay. I tell you how I would have done it, right? Because I'm a barefoot mathematician who has to do it always in a sort of the simplest possible way. I would have said, after 2 minutes, I've eaten 10, I've got 90 left. After 4 minutes, I still have eaten 10, I've got 80 left. 6 minutes, 10, I've got 70 left. 8 minutes, I've eaten 10, got 60 left. That's obviously, you know, I'm doing that on foot, not as elegantly as you did, but it gives me hopefully the right result. Yeah? Question for you. Can my number of sweets that I have in here, can it ever reach 0? Yes or yes? Yes. Okay, that was too easy. You don't get a sweet for that. Yeah, it can reach 0. If I plot this thing, where I plot number of sweets versus time, obviously the line would go up or down. Down, you're right. So it would look like that. Yeah? True that? This is here my starting concentration. And this is basically here when I have no sweets left. Very, very simple stuff what we are doing here. Just eating sweets. Actually, this is quite an interesting reaction that we are looking at here. Let's just simply quickly write down the rate equation for that. And I want to write the rate of this in a slightly different form. I want to write it as a change in A. And I symbolize this change with a small d. This means it's a very, very tiny, small change. A change in A over a change in time. And this d stands for really diddly squats. Very, very small. But it's the same as rate. dA over dt equals minus k times A. That's our general rate equation. And obviously I have to put in a rate order. And in this particular case, where the change is really constant, every 2 minutes I have eaten 10 of the sweets. The whole thing is constant, and therefore, in this case, I put a 0 here. This is actually called, very imaginatively, what would you call that? Let your creativity flow. What would you call this? It's a zero-order reaction, exactly. Thank you. Hope you like Bounty. So it's a zero-order reaction. And the equation for this zero-order reaction is actually the concentration of A at a given time, and I indicate that with a subscript T, at any time, minus the concentration at the starting time equals minus K times T at the time T, where we want to look at it, minus the time at the start. And I indicate that with a 0. So that is actually the equation for a zero-order reaction. And if that looks weird to you, I can write this in a slightly different format. I can write this as AT equals minus K times T of T minus T at the start plus concentration at the start. I just brought this minus A0 to the other side. What does that do for me? Well, again, it is the equation for a straight line. Y equals mx plus c. So what do I plot? I plot here A, concentration of A. I plot here time. This is this stuff here. And I get a straight line. This point here is this one, A0. And what's my gradient? Gradient is minus K. Bear in mind, K itself is always positive. K cannot be negative. The only exception where K is negative is when you are traveling faster than light. So in a warp drive, Starship, Enterprise, or something like that. Only then can K become negative. Now, since we usually don't do that, K is always positive. It cannot be negative. Okay? Are you happy with that? Fantastic. God, I'm so good. Right, now I've eaten my sweets. Somebody comes along and gives me more sweets, which is great, or cookies. No, we stick with sweets. It's easier. Okay, now I've got 100 sweets. But now my claim is that I can eat 10% of sweets in 2 minutes. How many sweets are left after 8 minutes? Here are some sweets at stakes. How many sweets are left? How many? 67. Who said that? 67? 66? 67? Well, we can't have half sweets. Huh? Who said it? So. Okay. Huh? You said 67.
Why didn't you
Naughty. 67. How did you do it?
Just take off 10% each time.
Just take off 10%. So let's do it slowly. So 10% is 10. Okay, yes, so we've got 90. Well, next time? Minus 9. I've got 81. Minus 8. Got 73. I can't take 7.3. I can't have half sweets. So I do 7. 67. Yeah? And that is 2, 4, 6, 8 minutes. After 8 minutes, I have 67 sweets left. 66. Who said 67 then? Okay, good. You really should give the... This is a bunch of cheaters there, huh? Can we ever have 0 sweets? In theory, if we round it always, yeah, we can get to 0. But if we are actually working with real numbers, we would never reach 0 because we could have half a sweet. And then 10% of half a sweet is 0.05. So you would have 0.45 sweets left, and so on and so forth. So, this is weird stuff, hey? Now, if we plot that, so here is the number of sweets. Here's time. What we would get actually is, will it be a straight line? No, won't be a straight line. Would be actually something like that. It would be a curve. You know how much I dislike curves. What? Jesus Christ, you have such a filthy mind. Now, in a mathematical sense, right, curves are not good. Make me blush. So how can we write this thing? Again, let's write our general rate equation. dA over dt equals, we have a consumption, so it's negative, minus k times A. Now we have a rate order, as we had in the other one. And this time it is 1. The rate order is 1. I'm not asking you what you would call this reaction, because it's pretty obvious. This would be a first order reaction. And the equation for that, slightly different to the one that we dealt before with. We bring in a wonderful new thing. It's the ln, natural logarithm of A at the time t minus ln at the time 0 equals minus k times t at the time t minus t at the time 0. And this is the equation for first order reaction. Now, if you don't like it that way, we can convert that again into a straight line. All I need to do is bring the ln A of 0 to the other side, and I end up with ln A at the time t equals minus k times t at the time t minus t at the starting point plus ln A at the starting time. What does that do for you? Well, we've got y equals mx plus c. So what do we have to plot this time? Remember, when we had our 0 order, we plotted A over time and got a straight line. For the first order, if we plot A over time, we get a curve. But if we plot ln of A versus time, then we discover that this thing has stopped working again. Okay, I think we are back. So if I plot ln of A versus time, then I get a straight line. Can this straight line actually go into the negative range? Can I do it like that? Yes? Who said yes? Who did? Sorry. Yes, it can go into the negative range. We see who is the... Yeah, good man. It can go into the negative range. It doesn't mean that the concentration of A is negative, which can't happen. It just can mean that here, in this range here, that ln of A is smaller than 0. But that's perfectly legit. And ln can be negative. A concentration itself can't be negative. Make sense? And actually here we have a nice method to distinguish between a 0 and a first order reaction. If we have a set of data, what we can do is, so let's say we have time and we have concentration of A. And we measure the time and the corresponding concentration of A. And we want to know whether this is a first order or a 0 order reaction. And what we can do is we can plot that. Okay, A time. I plot the data, and I get that. What kind of reaction is it? 0 order reaction. Exactly. Who said it? You said. You said 0. Oh, who said 0? Well, share then. Okay. So that would be a 0 order. What if it looks like that? What if it looks like that? Is that a 0 order? No? So it is? No. No. We don't know. We can only say it's not a 0 order. Yeah? There are more orders, and for example, a second order, which is perfectly feasible, would look like that. So if it's not a 0 order, our next attempt would be time, and now we do an ln of A. We see it's a straight line. If we see that's a straight line when we do ln of A versus time, then we know it's a first order. Okay? Does that make sense? Why do I tell you that? Where do we find first and 0 order reactions? Well, 0 order reaction, I observe that every day when I feed my dog. He is eating at a constant speed. Unfortunately, it's a Labrador. And Labradors have this annoying habit that I think they are missing a gene that tells them when they are full. So they eat constantly. Whenever there is food, it will be hoovered off at a constant rate. So, consumption of food in Labradors, that is a zero-order reaction. Interestingly, the degradation of alcohol follows a zero-order reaction. So when you go to the venue and you have a few pints or whatever, Jaeger bombs, your alcohol will be cleared from your body with a zero-order reaction. If you are male. With females, it's different. Females are more complex. Yeah, we knew it all the time, huh? But if you are male, it's a zero-order reaction. Where do we find first-order reactions?
Half-life.
Half-life. Excellent. First order. Where do we find half-life? Yes, radioactive decay. But also, many drug clearances from the body follow a first-order reaction. So detoxification or something like that, very often first order. Sometimes it's a second order, sometimes it's a zero order, but very often it is first order. Radioactive decay cannot be anything else but a first order reaction. I want you to remember that. Yeah? Now somebody said half-life. What on earth is half-life? Please write half-life. I had one person in an exam writing the low life. I thought, not entirely sure if I should give you full marks for that. But probably he was thinking of me. What is half-life? Well, half-life is defined as the time that it takes to go from A to half of A. That's a half-life. How can we actually calculate that? Now let's write down our equation for a first-order reaction. We said it's ln A T minus ln A at the starting time equals minus K times, and in this case we can, well, let's write it like that, Tt minus T0. If we just simply set our starting time as, that's when we start, we set this to 0. And this guy here, this T at the time T, that would be our half-life. And I write it like T half. And I can do something else. I can write this according to the rules of logarithm as ln a t divided by a 0. That's the same thing. ln at divided by a0 equals minus k times t half-life. Now, I can do something else with that. I can bring this negative sign to that side. And under the rules of engagement, under the rules of logarithm, I can write ln a at the starting time divided by a at my half-life equals k times t half. Now I can do something really nifty. I can say, okay, let's start with 100 sweets. And I want to see what's the half-life. How many sweets would I have after a half-life? How many sweets would I have in this case? After 50. Yeah, you're absolutely right. I deserve one. Can't even open it. That is, you know, that's called karma. So we have 50. K times t half. 100 divided by 50 is what? 2. You don't get a sweet for that. ln 2 equals k times t half. What's ln 2? T half equals ln 2 divided by k, just simply from this equation here. What's ln 2? 0.69, absolutely right. Oh, you had yours. You are in Russian. You only get one from me. Sweet, I mean. T half equals 0.69 divided by k. What if, instead of 100 sweets, we have 50 sweets? We start with 50 sweets. How many sweets have we left at the half-life? We start with 50. How many have we left at the half-life? About 25. Absolutely. 25. 50 divided by 25 is 2. So we have ln 2 again. In this case, the half-life is totally independent of how many we start with. And actually, you can do a nice trick. That is when people dealing with radioactivity. When is the radioactivity down to, let's say, roughly 1,000th of the original activity. Well, after one half-life, it's down to half. After two half-lives, it's down to quarter. After another half-life, after the third half-life, 1/8, 1/16, 32, 64, 128, 256, 512. After 10 half-lives, the radioactivity is down by a factor of 1,000 after 10 half-lives. So these are things that I would like you to remember. They could potentially come up in the exam. But you will get some exercises, how to deal with these things, how to calculate these things in the next few weeks. Any questions? Why didn't I get a sweet, hey? So the two people who answered the last two questions correctly, come and see me. You get your sweet. I know who you are. Have a lovely weekend. I don't see you next week and the week after because I will be at the pool thinking of you. Take care.